Fluids flow through soils, and the general understanding falls under fluid flow in porous media. In other words, for a couple of sessions, we're going to forget about the fact that the medium is made of grains. We're looking at the negative of the picture. We're going to emphasize on the pores, and these pores that are interconnected because they are determined by grains form a tortuous path, and that is where fluid flow is taking place. Today we would like to understand what is permeability. By the way, permeability is the property of the porous medium with that characteristic topology of the interconnected porosity. We also think of hydraulic conductivity, which is the rate at which water can traverse the porous medium, but is hydraulic, so it emphasizes on the properties of water. In fact, we tend to use these two words interchangeably, while in fact one is a property of the medium and the other one combines the properties of the pore topology and the characteristics of the fluid, in particular the viscosity. But please allow me, for simplicity, to use generally the word permeability, but they are actually different quantities with different dimensions. So please be alert when you read the literature. What is the physical understanding? First of all, go back and then remember Leonardo's parachute when somebody is falling from the sky, holding onto a parachute, and when that person is falling down, at the beginning it accelerates because it's subjected to gravity. And so the velocity begins increasing and increasing, but as the velocity increases, the weight remains constant, but the drag gradually increases. It gets to a point when the drag is equal to the weight, that the unbalanced force is equal to 0, therefore there is no more acceleration. And at that point, the velocity is constant. That is called the terminal velocity. What we're going to do today is to analyze fluid flow in porous media at constant velocity. In other words, assuming that there is no global acceleration, even though you recognize that there are internal accelerations taking place. So let's consider now a tube, and this tube experiences a fluid flow, and the analysis of equilibrium, because the system is at equilibrium, is such that the driving force, which in this horizontal tube will be the pressure gradient, in an inclined tube is the total energy, including the self-weight. So in this horizontal tube will be a pressure difference that is driving the fluid, and what is slowing down is the same as Stokes' drag. And so there will be a drag force acting that the walls exert on the fluid, and there is a pressure difference that is driving the fluid flow, and these two are at equilibrium. So if we take it for a slice, but furthermore we're going to take a subset of this tube, we're going to look at a ring inside the tube. So this ring has a radius r, while the tube has a radial capital R. Then for that ring, let's do the force equilibrium. From the left, you have the pressure U acting on pi r squared, and that has to be equal to the resisting forces from the right, which is the pressure has decreased according to the gradient, so plus du dx, if this is in direction x, times dx. This is the gradient times dx gives me the change of the pressure times pi r square. And the drag force, which is acting on the perimeter, which is going to be equal to tau times 2 pi r, and all this is happening for the length dx. This is indeed the summation of forces equal to 0 for a system in a steady state flow, that means at equilibrium at terminal velocity. Now we can see that this u pi r square will cancel with that one. Therefore, du dx pi r square, and change the sign, and this dx will cancel with that dx, will be equal to tau 2 pi r. Dx cancels out, and this one cancels out with that one. Now, tau is the shear resistance of a viscous fluid. So from Newton's equation for viscosity, tau is equal to the viscosity times the shear rate. And the shear rate is equal to the shear, which is the deformation, the distance that it travels in L differentially along the radius. So this is the shear distortion, which is dl dr over rate, over time. Now, dl dt is velocity, so this is going to be equal to mu dl over dt is a dv, d change in velocity dr. Now we can replace in this equation, but once again remember that du dx is a pressure gradient, and pressure is related to the pressure head and gamma water. So this is d h pressure over dx gamma water r is equal to 2 tau, where the tau is going to be replaced by mu dv dr. Now, without loss of generality, this was done for the horizontal one. I realized that if it will be inclined, once again, I will consider the self-weight or the changes in elevation. So I also have to put the elevation head. So I can generalize that to become the gradient. And so I can say that minus the gradient times gamma water r is equal to, and then I divide by 2 mu, 2 viscosities, is going to be equal to dv, and now I multiply both sides by dr. And that is how the velocity changes with the radius across this tube. So I can integrate, and I'm going to do this from 0 to r, and so I'm going to get that the velocity will have a term that is a constant that I have to solve for. So this will become the velocity is going to be equal to r squared over 2. So this will be minus the gradient in gamma water r squared over 4 mu plus c. That is the velocity profile, and already tells me something very important, that the velocity profile will be parabolic across the section. Now the problem is what is c, and when I evaluate this equation, when r is equal to r, so at r is equal to r, now I'm going to assume non-slip on the edges. And so at r equal r, v is equal to 0, and therefore c is equal to I gamma water R over 4 mu. Now I can replace and I get the equation for velocity as a function of the radius, which I'm then going to integrate to get the flow rate along the tube. So we concluded that the velocity profile within the tube has this parabolic relationship where when the radius equals the wall, the radius to the wall, the tube size, the velocity goes to 0 because we have adopted a non-slip boundary condition. Now, what is the amount of flow that will go through the tube? Well, then it will be the integral of the velocity at distance r times an annulus where at distance r, where that velocity is taking place, which is going to have an area of 2 pi r dr. When I replace this velocity with that velocity and I integrate, now I will conclude that the velocity in the tube is equal to pi gamma water I over 8 viscosities times r to the 4th. Why? Because there is an r squared times an r becomes r cubed. When we integrate from 0 to r, then it becomes an r cube. This is the flow rate along a tube of constant diameter subjected to a gradient I of total head when the fluid has viscosity mu. This omega is the subindex of to indicate that is the water unit weight. If this was not water, it would be the proper densities and viscosities, or unit weight and viscosities of the corresponding fluids. This equation is known as the Hagen-Poiseuille equation, and it is a fundamental equation to understand fluid flow. Look, folks, it's telling us that if we replace a soil porous structure by a sequence of tubes, the largest tubes will control the flow because their effect goes to the 4th power of their size. And so, in fact, let's do that. Let's assume now that we have a soil block that is actually made of tubes. Instead of having the true porous network of soils, in this plug of soils, there are a total of n tubes for a cross-sectional area A. What is the equivalent permeability of the soil? Permeability is equal to KIA according to Darcy. This is the macro scale definition, and this is the permeability, or better said, the hydraulic conductivity, which by the time we review it in terms of parallel tubes of equal diameter, this will be equal to the number of tubes times the flow rate in each tube that comes from Hagen-Poiseuille. So that means that permeability is going to be equal to number of tubes over the cross-sectional area, since this is the density of pores, times Q tube over the gradient, which from Hagen-Poiseuille you already begin to see what it is. So let's begin replacing it. Once again, notice that we're going from a macro scale definition and we're trying to relate it to a micro scale conceptualization, upscaling it in a fairly rudimentary way. So by the time we replace with Hagen-Poiseuille, this becomes n tube over area times K over I becomes pi gamma water I over 8 viscosities R 4. So this is K tube, this is K tube, over I is pi gamma water over 8 viscosities R. Now, we really don't know the number of tubes per area that we can count on, so let's see how can we gradually replace it. From the macro scale, it will be interesting to recognize two things. First of all, what is the surface area that is available? Because going back to Leonardo's parachute, it's all about drag. Permeability is all about drag against the walls. And that means that we need to know how much area of walls we have. So the specific surface is equal to, each tube has an area of 2 pi r times the length. Let's say this is the length of the plug. 2 pi r L is the surface area of each tube times the number of tubes over the whole mass, which is area length times rho of the material dry. And so notice that L cancels out and NT over A appears. So this is 2 pi R over rho dry NT over L. So now, interestingly enough, we can go back and replace this NT over L here to conclude that the permeability is equal to, let's first of all write this part, which is pi gamma water over 8 mu R to the fourth. And now we are going to replace NT over L by specific surface times rho dry over 2 pi r. But we still have an issue that we have r, and we would like to have one more replacement in terms of macro scale parameters. And so let's look at another macro scale parameters, the porosity. The porosity is equal to the volume of voids over the total volume, and the volume of voids is pi r squared, the area of each tube times the length of each tube times the number of tubes over the total volume, which is area times the length. So the length cancels out, and here I have NT over A. So this is pi r squared NT over L, but NT over L, we already said that it was equal to rho dry times the specific surface over 2 pi r. So pi r r, and this is equal to rho dry specific surface over 2 r. Now here this was simplifying to pi, was cancelling with pi, r with r cubed, and so now I can say that this is gamma water specific surface rho dry r cubed times 16 mu. Now the r cubed from porosity is equal to 8 n cubed over specific surface rho dry cubed, which simplifies to specific surface rho dry cube. With this one becomes a square, and I have now the 8 with the 2, and this becomes gamma water times over 2 mu times n cubed divided specific surface square rho dry square. Now, rho dry is the mineral mass density times 1 minus the porosity. So we can write this further by saying that this is gamma water over 2 mu specific surface square n cubed over rho mineral square 1 minus the porosity square. And this is a wonderful expression. This is the permeability that is Darcian permeability, in fact is hydraulic conductivity to be precise, computed from the pore scale analysis where we replace the soil porous network by a series of parallel tubes of equal diameter. And the final solution is that it is proportional to the porosity, but it's in a weird ratio. It's n cubed over 1 minus n square to the square, but it's also inversely proportional to the specific surface squared. And so these are parameters that we can readily measure. We measure the porosity very easily, and we measure the specific surface very easily, and these equations tell us that they are going to govern the effect. But as you will see, n cubed over 1 minus n to the square has a minor effect compared to the prevailing effect of a specific surface. This equation is called the Cosseni-Harman equation. So this board really has quite a fascinating set of equations. The first one, we understood what is the fluid flow through a pore, through a tube of constant diameter, and we realized the importance of the tube diameter on the flow rate for a given gradient. The tube radius or diameter has a power of 4. That means that large tubes will have a very important effect on flow compared to smaller tubes. The second part of these derivations consider the soil mass and the pore structure as a series of parallel tubes, and let's start by saying they are of equal diameter. If that is the case, now we can add up the contribution of all tubes to get an equivalent definition of the hydraulic conductivity, and by doing a sequence of replacements, trying to go from pore scale parameters to macro scale parameters, we were able to find an expression for the hydraulic conductivity in terms of a series of a parallel number of equal diameter tubes in terms of the porosity and the specific surface, where we highlight the role of specific surface, the amount of surface in the pore plug along which the fluid will have to rub, creating the drag that will control the resistance to fluid flow. You can go back to earlier videos where we show that the specific surface is controlled by the smallest dimension of grains and increases quite dramatically as particles become smaller. So does the permeability.